Hi everyone, welcome to our webinar about Kubernetes-native database schema migrations. My name is Rote. I'm the CTO, co-founder of Ariga. I'm maintainer of two popular open source projects. One is Ant, an entity framework for Go, and the second one is called Atlas, which is the topic of our webinar today. Atlas is an open source schema migration tool, sometimes been called Terraform for databases, but basically it's a tool that tries to apply modern DevOps principles to the domain of schema migration. So, what do we have planned for today? We're going to kick off by discussing the concept of continuous delivery and how it applies to database changes. Next, we'll show some anti-patterns and stuff that maybe you shouldn't be doing when you're deploying migrations. And finally, we'll discuss at length the Kubernetes native way of doing schema migrations. Spoiler, it's not going to be one answer, but we'll show a bunch of approaches that might work for you. And let's get started. We begin our discussion by trying to answer this question. Why do we need continuous delivery for databases? Now, no discussion of continuous delivery can be complete without us mentioning Accelerate, this super interesting and important book by Nicole Forsgren, Jez Humble, and Jim Kim. Is considered by many the Bible of DevOps philosophy, and the important thing is that it's not a philosophical book. It's based on lots of scientific research that checks and quantifies the correlation between different DevOps practices and the business outcomes. And this is what the authors have to say about continuous delivery. A key goal of continuous delivery is changing the economics of the software delivery process so the cost of pushing out individual changes is very low. So the core goal of CD is to make change cheap. Normally, or before CD, deploying to production is an error-prone, stressful, time-consuming, resource-consuming process. And the goal is to make the cost of making any one change to the system very, very cheap. Now, how do we achieve this wonderful result? Well, according to the authors, the key capability that organizations need in order to achieve continuous delivery is something they call comprehensive configuration management, which they state it should be possible to provision our environments, build, test, and deploy our software in a fully automated fashion, purely from information stored in version control. Now, many of you may be familiar with the concept of GitOps. Well, this is it. Our entire system can be automatically be provisioned, tested, deployed, and everything entirely from information that we store in source control. So why is continuous delivery so great for your teams? Well, once you make change cheap because it's fully automated, you no longer have an incentive to batch a bunch of changes together, which means you can roll out much smaller changes. Now, another great property of small changes is that they are usually reversible because you can pick any single commit in your Git history and it's going to involve very few lines that you need to revert. So by having completely automated deployments, we're able to make smaller changes, reversible changes, and make our team much more nimble, agile, and flexible. Okay, so I think we've established that continuous delivery is a positive thing, that it's good to automate your deployments. But why are we talking about the database? Why do we need CD for databases? Well, it turns out that the answer is very simple, but it may be not intuitive for everyone. The truth is very simple. Evolving your application means evolving your database schema. Your application, 95% of the time, is backed by some database. This database has a schema. As you add features, you need to create new tables. You need to alter the table structure. You need to add indexes to improve performance. Evolving your application means evolving your database schema. Well, if your database is part of your infrastructure, part of the dependencies of your application, you should, in theory, automate them entirely. Well, it turns out that while this is true in many organizations, in many companies, in many software engineering teams, this is not yet the case. They're running a Kubernetes cluster, they have maybe a Terraform infrastructure as code pipeline, but the database is somehow left out of this thing. Finally, let's discuss what we came here to talk about, which is how to deploy migrations, how to deploy schema changes when we are working with Kubernetes. There is nothing software engineers enjoy more than having strong opinions about why something is wrong to do. So with that, let's start with a couple of anti-patterns. The first one, which we mentioned before, is running migrations manually. Running the database commands needed to upgrade your database version from the previous to the next in a manual or semi-manual fashion. This can mean opening a terminal to directly connect to your production database and type out the commands by hand. It can mean running some script or tool, but initiating this process in a manual way. The benefits of continuous delivery come from having a holistic, complete capability to provision your entire infrastructure in one automated flow. If it requires human intervention, you're missing out on a lot of benefits, such as automatically provisioning environments, running tests, running automated deployments in the background, doing rollbacks when stuff fails. You need to be able to pick some, commit in your Git history, and deploy from there. The next point I want to cover is something I've seen very often, which is running migrations as part of your application. This means that when your program starts, before the server starts listening on some port or before the main business logic start, the application from the application code runs the schema migrations to update the database schema. Let's discuss some reasons that make this an anti-pattern. First of all, attack service. If you bundle an extra tool and all of its dependencies into your main container in case your application is compromised, your attacker has way more to play with than they probably should. Second, you should not use the same database connection, the same user and password for changing the database schema and doing runtime operations. So it's better to separate them into two containers. Second, when migrations fail, and they sometimes do, your application can basically not start up. So if there is some pod that is running your application, the application first tries to run migrations and then fails, you basically now have a pod that is useless. Depending on your deployment rollout strategy, this crash looping may cause a reduced capacity of your application. Finally, migrations must be synchronized. You need mutual exclusion. You cannot have two containers racing to perform the migrations. So if you have 100 containers and all of them during initialization try to migrate your database schema, you're either going to need to mutually exclude them, meaning they must load one by one, you're going to wait for the lock to start working, or you're going to need to change your deployment rollout strategy to effectively be one by one. But this really becomes a limiting factor into how fast or how much flexibility you have when making decisions about rolling out your application. Okay, with these out of the way, let's discuss some guiding design principles for building our deployment pipeline for schema changes. The first one is that schema changes should be versioned, deployable artifacts. In the same way that when your application code changes, you create a Docker image, a version Docker image that corresponds to the specific version, so you can deploy it specifically to production. In the same way, you should create deployable artifacts that are derived from source control and are accessible to your production system, so Kubernetes can deploy your changes to your database. The second principle I want to discuss is that database schemas should be treated as infrastructure in the same way that your application may depend on an S3 bucket existing or some IAM role be provisioned so it can use it to access resources on AWS. In the same way, the schema of your database is a prerequisite for a version of your application to work. Therefore, you should treat it as infrastructure, which means it should be deployed as a discrete step before your application starts deploying. Finally, the third principle that I want to present today is that deployments should halt on migration failures. Migrations do fail for various reasons, and what you should do in those cases is that you should not roll out your application if schema migration fails. So the first thing we need to do before we can actually start deploying schema changes, we need to create these deployment artifacts. Now, I want to suggest a couple of ways you can do it. Of course, there are many other ways that you may come up with, and they are all fine. The first one is to create a custom migration image. This means that during your continuous integration pipeline, whenever you merge changes to your main branch, you're going to build a container image. Its base is going to be Atlas, so it's going to contain the Atlas binary, which is going to run your migrations. And you're going to copy your migrations directory into this image so you can basically access it during runtime. The important thing is to give this image the tag of your GitHub commit SHA or whatever versioning scheme you're using it, so it can be correlated with the application version that you're going to deploy. The second way, which also works great, is to use Atlas Cloud. Atlas Cloud is our cloud offering for Atlas, and it's very easy to set up Atlas Cloud in such a way that whenever you merge changes to your main branch, the migration directory is updated and it's revisioned, and you can reference a certain revision of your migration directory from Atlas to deploy it directly. Finally, you can use a custom volume mount instead of copying the migrations during continuous integration. You can do it in runtime to mount it from a config map or a Git volume or whatever way that you want. If you search online for advice on how to run migrations in Kubernetes, eventually you're going to hit this suggestion: use init containers. Now, what are init containers in Kubernetes? If you have an application deployment definition, for example, this toy example is just deploying an Nginx container. An init container is a container defined to run before the main container runs. Now, the rule is that if this container crashes, the application will not start, which satisfies our requirement that if migrations fail, we should not continue rolling out our application. Now, let's see how to use init containers to deploy migrations with Atlas. So we start out by creating a configuration file that contains the credentials to the database. We then create a secret containing this data and apply it to the cluster. Once the secret is created, we need to create a volume definition that basically makes this secret available to our deployment pods. And finally, we create the init container. Let's look at the definition. It's going to use a Docker image that we built beforehand that contains Atlas and our application migration directory. Notice that it's versioned. In practice, you will probably use your Git commit SHA, but you can use any versioning scheme that you like. And finally, we need to pass some arguments to Atlas so it knows where to find the database credentials and where to find the migration directory itself. Of course, our configuration file, which contains the database credentials, needs to be mounted to this container. Otherwise, it will not know how to connect to the database. Okay, let's take a moment to analyze this option of using init containers to run schema migration. So the good thing is that the migration context and the runtime context are going to be separate. Because we're going to use different containers for each step, we don't need to provide runtime with a role that has too much power on our production database. And of course, we don't need to bundle extra unneeded dependencies to our runtime environment. Something that's not exactly good and not exactly bad is that we achieve the goal that failed migration will halt the deployment, but it will not look pretty, because if our migrations fail, basically we will have a bunch of pods that look inside Kubernetes as crash looping. This can have negative impacts, as we discussed earlier. And finally, what we don't achieve with this setup is that migrations don't run as a discrete step, meaning that each pod still tries to run the deployments on its own, the migrations on its own, which means that if we have lots of replicas, they're going to be racing one another or synchronizing the migration runs with one another, which slows down our deployment and introduces other issues, as we've discussed. Next, let's discuss another popular way for deploying schema migrations to Kubernetes, and that is using Helm. Now, if you haven't used Helm before, Helm is a package manager for Kubernetes that allows us to bundle all of the resources relevant for our application in one artifact that is called the Helm chart. Now, what we're going to do in this example is basically to use a very cool feature in Helm called lifecycle hooks that allows us to create resources in specific lifecycle events in our application deployment. Specifically, we're interested in the pre-upgrade hook, which upgrades on an upgrade request after templates are rendered, but before any resources are updated. So what we're going to do is create a Kubernetes job. This is a one-off container, one-off pod that's going to run. We're going to annotate it with these annotations, pre-install and pre-upgrade, so before our application rolls out. And we're going to add this deletion policy so Helm knows to clean up our jobs after they are completed. Our job is just going to run migrate apply on the pre-existing container that we already created. Okay, let's take a moment to analyze this option of using Helm pre-upgrade hooks. So the migration context is separate from the runtime context, just like we saw with Initcontainers. Failed migrations do halt deployments in an elegant way because the deployment will not even begin unless the pre-upgrade hook ran to completion. And finally, migrations runs as a discrete step, right? The hook is its own step. It does not start a million containers that try to migrate the database schema, and this basically works perfectly. Now, this is great. We've actually used this setup at Ariga for a very long time, but still it's kind of yucky and it can be improved, and we'll try to show why.
Setting up migrations with Helm pre-upgrade hooks does work, and in fact, at Ariga we worked this way for a very long time. But it does leave the question of, can we do better? Let's consider some issues or complaints that we received from the community about this workflow. First of all, it feels a bit cumbersome. Checking in my migrations to Git, building a Docker image, setting up the pre-upgrade hook and defining the job, making sure all the secrets are in place, and only then get to my application being deployed. Second of all, Helm, since version 3, is entirely client-side, which means that there's no controller running in the cluster that's responsible for this workload, which means, and this happens very often, is that if something times out or doesn't work the way we intended to, Helm does have a tendency of leaving these jobs dangling around the cluster and require some cleanups, which is not super elegant. And finally, if you've seen what's happening in the Kubernetes ecosystem, you know that Kubernetes is really extendable with custom resources, CRDs. And the current solution we propose is semantically opaque to migrations. Our cluster is dealing with jobs and secrets, but it doesn't have a semantic representation of what's going on, which makes it harder to build tools and more interesting workflows on top of this. To really push the envelope on what's possible with regards to doing schema migrations in Kubernetes, we have recently released the Atlas Kubernetes operator. The Atlas Kubernetes operator creates two types of custom resources in your cluster. One is called an Atlas migration, which is used for a version migrations workflow like we've been demonstrating for since the beginning of this webinar. And the second one is called an Atlas schema, which is used to create a declarative migration workflow, which we will discuss in a few minutes. Let's showcase this by demonstrating an end-to-end flow of using the Atlas operator with Atlas Cloud. You don't have to use Atlas Cloud with the Atlas operator. There's plenty of other ways to do this, but for a short demo, this can showcase a lot of the possibilities. So our plan is to deploy the Atlas operator to a cluster. You can see we're running a local Minikube cluster that we're going to be playing around with. We're going to deploy a dummy database, a MySQL database, to this cluster. We're going to connect this repository we're working in to our Atlas Cloud account. Finally, we create an Atlas migration resource, which is a custom resource that defines a policy for running version migrations. We're going to show some end-to-end runs of how this thing actually works. So let's start by installing the Atlas operator on our cluster. So the Atlas operator is available as a Helm chart that you can install on your cluster. And let's just check that the operator is running, and we can see it's still creating the container. If we wait a second more, we can see that the Atlas operator is ready and is running in its own namespace. So this is done. Next, we have a YAML manifest here defining a simple deployment for a MySQL deployment. It's going to run the standard MySQL Docker image, set some basic credentials via environment variables. It creates a service that exposes our MySQL pod via a Kubernetes service. And finally, we're creating some secret here with the connection URL to our database. So let's go ahead and apply this manifest. Let's see, and our resources are created successfully. Next, let's connect our repository to Atlas Cloud. So what I have here is some basic Atlas project that I bootstrapped from the Ariga Atlas template repository that gives you kind of a starting point for an Atlas project. You don't have to use it, but if you want to play around with this stack, it's a pretty good choice. And what I'm going to do next is connect this repository, this migration directory containing my migration files, to my Atlas Cloud account. So I've created an Atlas Cloud account a few minutes ago. It takes less than a minute. You can log in with your GitHub account and get started really quickly. Let's now connect our migration directory to our Atlas Cloud account. So I'm going to use the GitHub app option. I've already authorized the needed permissions to do this. And let's look for our Kubernetes demo repository. Here it is. Now we need to select which migration directory we want to use. So we are going to use the migrations directory, which contains our migration files. And we're going to give this name case demo. Okay, we are using Atlas for this as the format of the migration directory, and as you've seen before, we're going to connect it to, we're going to deploy to a MySQL database. So now let's click connect, and our migration directory is now connected to our account. When this integration is ready, meaning when my migration directory is connected to my cloud account, whenever I push changes to my main branch, to my master branch, this screen is updated. The current version is pushed to my cloud account, and I can use it to deploy my migrations directly from this account. Since I want to deploy migrations directly for my cloud account, I'm going to go to the deployment screen and see this getting started workflow where I can generate a token and get suggestions on how to deploy from my cloud connected directory. I'm going to generate a token. I'm going to copy this. There is here a suggestion of how to do it directly with the command line, but this is not the workflow that we're interested in. We want to use the Atlas operator. Let's see how to do that now. Okay, so we've connected our repository to our Atlas Cloud account. Our next step is to create an Atlas migration resource for our migrations. Now, first thing we're going to do is to create a new secret. This secret contains the token for the cloud account bot that we've just created. And the second resource we're going to create is an Atlas migration custom resource. We're going to name it demo, and we give it two interesting configuration bits. One is URL from. This is a reference to our MySQL credential secret, which contains the connection string to the database. And we're going to configure our cloud account and the token for our cloud account, which we're going to take from the Atlas credentials secret that we've just shown. And finally, we need to tell it information about the directory that we want to be using. And this is a remote directory stored in Atlas Cloud. And if you recall, we named our directory Kate's demo. Now, if everything works correctly, we should be able to apply these resources and see our migration take place. So our existing resources are unchanged. We have created a custom resource for our migration, and we created this secret that we need. Now, let's try to see that this thing actually exists. I really enjoy using this K9s project to get a easy to use a view of my cluster. Let's see all the resources in our cluster. We want to see Atlas migration resources, and we can see that we have this demo resource within a ready state. We can see the YAML representation of this resource. If we scroll to the bottom, we can see that this migration was applied successfully. Now, don't take my word for it. Let's run a small query to see that this actually works. Let me just pull up this command that's going to connect to the database and print the database schema. Let's see. We can now see we have one table called users, and here are the fields that are supposed to be there. So what just happened here? I think it's pretty cool. So if you recall, we synced our migration directory to the cloud. We created a token for the Atlas operator to use. And then we created a Atlas migration custom resource that references this command. Now, whenever Atlas runs a migration using Atlas Cloud, it will actually report the results of this run to the deployment screen. And here we can see our migration that was applied successfully, and we can see all of the files and the relevant logs. This screen is also super useful when something goes wrong and you want to debug your migration. Okay, so we've created an Atlas migration resource. We saw our deployments run, And now let's show briefly end-to-end change and what does that look like in this workflow. So let's check out our change branch and make some things. So let's create a new migration just to simulate the workflow where we create and we make some change to our schema. And just to keep things simple, create a table P with a single column, and that's it. Okay, so we have our new migration file, and the Atlas sum file is updated. And now let's push this change to our new branch and table C. Now, the moment we create a pull request, Atlas Cloud kicks in. Because our migration directory is connected, we can see that Atlas immediately runs a lint report, and let's see what it has to say about our change. So turns out that we have some mistake in our SQL. So let's check ourselves again. Let's verify this statement, and obviously create table is the correct syntax. We need to rehash our directory. Let's put this change, my mistake, push the change again, and go back to our pull request. Now, this all happens pretty quickly, but as soon as we make a change, we can see that Atlas Cloud kicked in, and we can see its review. So it ran an integrity check, it checked, it replayed the migration file and made this analysis. Nothing was found. We can see this also on Atlas Cloud, and we can see that all of these tests ran and nothing interesting was found. So guess what? We can now merge this pull request and go forward to deploying it. So we can delete this branch as soon as our our main branch is updated. We expect to see in our migration directory that this file is updated, and you can see it's already here, our T table. The next step, of course, is to deploy our migration to the database, to our cluster. However, if we simply run kubectl apply, you'll see that Kubernetes says that this resource is unchanged. Now, if we look at the manifest itself, we see that indeed it does not change, because what changed is some external resource that external to the cluster Kubernetes cannot know about this. Now, the Atlas controller will run a reconcile loop every once in a while in the background. Eventually, this difference will be reconciled. But if you recall before, we discussed about the great importance of having the migration artifacts revision. These artifacts are stored in Atlas Cloud, and to tell the Atlas operator specifically which version we want to deploy, we need to supply this this tag field that tells the Atlas operator specifically which version to run. This is very important to do this in your system so that it is explicitly defined, hermetically defined, which version you are referring to. Now, once we apply this, we can now go back to Atlas Cloud, and we can see our migration file was successfully executed with our create table T statement. Now, if you've been listening so far, you may have noticed that I did omit something really important that I've been preaching for this entire webinar, which is I didn't show you how your CD pipeline is supposed to wait for the Atlas migration resource to be ready before you continue to roll out your application deployment. Now, to address this, and because we are a bit short on time, I'm going to squash together two discussions. One is we're going to discuss the declarative migration approach, which is completely different from what we've shown so far. And the second one is how we're going to use Argo CD to orchestrate our deployment such that we wait for the Atlas resources to be ready, only then move forward with the application deployment. Let's do it. I now want to discuss an alternative workflow that is called the declarative workflow. So far, we've demoed the version migration workflow, which many of you probably used with other tools in the past, which is the classical migration directory. I'm going to, ahead of time, define the changes in the database. And the only role the tool has basically is to run the migration that will not yet run on a target database. Atlas supports an alternative workflow, which is much more similar to the way Kubernetes itself operates, which is a declarative workflow. In this declarative workflow, we first define the desired state of the database. So, for example, the create table statement of defining the different tables that we expect to see. And Atlas, the Atlas operator, will run a reconciliation loop to calculate the diff, what commands need to be executed on your database to reconcile between the desired and the current state of your schema. Now, this may sound really scary to you, and you're probably thinking, how do we know that Atlas is not going to go crazy on our cluster and start dropping resources? Well, your fear is justified, but we have baked a lot of safety features into Atlas to let you control the way that it calculates diffs and to disallow it from doing certain kind of changes. Let's see now how this. So when using the declarative flow with the Atlas operator, you basically can define two kinds of policies that direct Atlas exactly how you want it to plan your changes. And these are diff policies and lint policies. Diff policies basically say, okay, Atlas, after you have calculated a plan, I want you to modify it according to some policy. And the main one that I'm going to show here is the skip policy, right? We can tell Atlas to skip certain changes, for example, to disallow it from dropping columns. So whenever Atlas tries to reconcile between your current and desired schema, if there is a column that exists in the database but does not exist in the desired state, it will edit this part out. So you can limit it from making destructive changes. The other kind of policy is called a linting policy, and it works a bit differently. Linting policies basically evaluate the plan before it's being executed, and if it violates some part of the policy, it will cause the migration to fail. So in this case, we have a linting rule that says if you encounter a destructive change, a change that will lead to data loss, for example, dropping a table or dropping a column, then you must stop the reconciliation loop. And you will see that the resource is not in a ready state and migration has halted. For our final demo for today, we're going to show how the declarative workflow on the Atlas operator works with Argo CD. And hopefully it will also answer our question before about how to make sure that migration is run before your application upgrades. Now, we're going to do this with Argo CD. If you don't know Argo CD, it's a Kubernetes-native continuous delivery tool that implements GitOps principles. It uses a declarative approach, and it has a really nice UI for running deployments to Kubernetes. And this is how it goes. So on a high level, we're going to have a backend application that's going to be simulated by a simple Nginx container. We're going to have our MySQL database as the target database, same as our example before. We're going to have a desired schema, an Atlas schema custom resource defining how we want the schema to look like. And of course, we're going to have the Atlas operator and Argo CD running the show. So how do we run schema changes in an Argo CD deployment? Similar to Helm, Argo CD has a concept called sync waves, which basically allow us to annotate, to provide an annotation on each resource and tell Argo CD this resource belongs in sync wave 0. This resource belongs in sync wave number 1. This way, we can break down different resources into different steps and not move forward with the deployment of one step before the previous one completes successfully. In our case, we're going to start by provisioning the database instance in step 0. We're going to then migrate the database schema in sync wave 1, and finally upgrade our application code in sync wave 2. To get started, let's start by installing Argo CD. I've already done this before to save time, so applying this manifest should be very quick. We can, of course, wait for all of our pods in this namespace to be ready. This is already ready from beforehand. We, of course, need to install the Atlas operator, same as we did before. We don't need to do that because it's already installed on the cluster. We can show that it's already ready by using kubectl wait. Next, Argo CD works best by referencing some Git repository that contains the desired state, the desired configuration of the application. For this demo, I created this GitHub repo that contains all of the manifests required for the application that we show here. But let's break them down now. So we are going to start describing our application with the target database. This is very similar to the demo we've shown before. We're going to define a service that exposes our database and a deployment that's going to run a MySQL container, which is going to act as our target database. In this demo, notice that all resources are always annotated with their respective sync wave. The next thing we're going to define is the Atlas schema custom resource, which has this SQL field that defines the desired state of the database. Notice that this resource is annotated with field number 1. Finally, we are going to show our Nginx deployment. This is just a placeholder for what would be in your use case, your own application. Next, let's answer the question of how Argo can know to wait with starting sync wave number 2 before sync wave number 1 is done. Now, Argo CD natively knows about health checks for native Kubernetes resources like pods and jobs, but out of the box, it does not know anything about our Atlas schema custom resource. So we need to provide it some way, some logic to know when to consider our Atlas schema resource as healthy, because otherwise it will just not check anything and move forward with the application rollout before our database schema is ready. Now, it turns out that Argo CD understands Lua, and you can use this scripting language to give it a simple piece of code to decide whether the application is healthy or whether it is degraded. The Atlas schema exposes a condition called ready, which is pretty standard in Kubernetes, and only when this condition is status is equal to true will Argo CD consider our custom resource to be healthy. Finally, we need to create an application resource that kind of ties between our Git repository and our Kubernetes server. Once we deploy this, Argo will kick into action and start deploying our application. Okay, now that everything is prepared, we can start deploying stuff to our cluster. So let's start by deploying the Argo CD config map that contains our new health check. This instructs Argo CD how to treat our special Atlas schema resources. Next, let's deploy our application. This once this happens, we can go to the Argo CD UI and look at how this deployment actually rolls out. So it starts, of course, with sync wave 0, with deploying our MySQL service and deployment. As soon as the health check for that is healthy, it's going to start with sync wave number 1. And you can see now that our Atlas schema is not healthy yet, which is why it has not started to deploy the Nginx pods. Once we can look into this. Once this schema is ready, which is now, we can see that Nginx starts to roll out. And as soon as this health check is ready, our deployment is successfully synced and everything is done. Okay, that was a lot of Kubernetes demos. I hope that at this point, at this time, you're still here with me watching this webinar. To recap, we have demonstrated different approaches for deploying schema changes to Kubernetes. We went through Initcontainers, we went through Helm charts with pre-upgrade hooks. We showed a demo that shows how to tie Atlas Cloud and the Atlas operator to run version migrations on your cluster. And finally, we did an end-to-end demo of what I believe is the future of schema migrations, which is declarative workflows with the Atlas operator tied with Argo CD to orchestrate the deployment. And I think this is really exciting stuff. So as we promised, after this presentation, we're still hanging out here to answer any questions. And if you're watching this after the fact, you are, of course, welcome to join our Discord server. We have a special channel for Kubernetes related questions. So please join us there and join the conversation. Thanks a lot for watching. I hope to see you in our next webinar. Goodbye.